So what we're going to look at today, we're going to continue our examination of circles, right? We're going to continue talking about angles today too, all right? So if you would look in your book on page 805, or section 15.3, page number 805, 805. All right, so on page 805, we're going to learn a little bit of new vocabulary, okay, and then we're also going to talk about some angles that are formed with this new vocabulary and how it relates to arcs on the circle and stuff like that, okay? So the title is Tangents and Circumscribed Angles, okay? We've already talked about inscribed angles. Inscribed angles are angles whose the vertex is inside the circle, right? The vertex, is on the circle. The vertex of this an inscribed angle is on the circle, and the angle is kind of inside the circle, right? A circumscribed angle, the vertex is going to be outside of the circle, okay? And you get some relationships and stuff from that, okay? Or potentially on the circle too, but anyway. So what are the key theorems about tangents to a circle? Now this word tangent, right? It's like that word tangent that we use when we're in trigonometry, and in fact there is a relationship between those two words, but it's not so obvious, okay? But there is a relationship between those two words, but we're going to kind of keep them separate for right now, okay? And for the class, I mean, yeah, you don't need to necessarily know how they're related, but anyway. So a tangent is a line in the same plane as a circle that intersects the circle in exactly one point. So you can see here's an example, right? Circle C, okay? This is a tangent line right here, or just a tangent, okay? The single point where that line intersects the circle is known as the point of tangency. Okay? This idea of a tangent line and point of tangency, right? It shows up in geometry. It'll also show up much later, again, if you decide to take calculus, okay? It's going to be something important for calculus as well, okay? But for right now, a tangent line has just one point in common with the circle, okay? Like that, okay? So, we've got all that right there. We're not going to go through the investigation here again. We're just going to jump right to the theorems and stuff, okay? But as it turns out, if a line is tangent to a circle, then it is perpendicular. That means it makes what kind of angle? A right angle, 90-degree angle, to a radius drawn to the point of tangency. So here's our tangent line, right? There's our point of tangency right there, where that line intersects at the circle exactly one spot. And our radius, if we draw a radius from the center to that point of tangency, you can see that we form a right angle with those two segments. Hello? Hey, I didn't give them, I just said that was the homework, and then I said work on your problem set, and then I'm going to post the test review today too, so. Alrighty? All right. Bye. Okay, so let's take a look at this here, right? So we're not going to prove this either, but we'll get into some other stuff here. I do want to jump down right here, though. So knowing that on the bottom of page 806 here. So knowing here, so both lines in the figure, so both line here and line here, okay, those are tangents, okay, to the circle, and AB is a diameter, okay? What can we conclude, you think, about these two tangent lines here with this relationship? What do you think is going to be true about these two lines? They're going to be what? Eli? Parallel, exactly right, okay. How can you say that, Eli? What's kind of cluing you in there? I mean, they look parallel, obviously, but what kind of like... Okay, and they're both perpendicular to the same line, right? This line is perpendicular to segment AB, which is also... This line is perpendicular to that same exact segment. Yeah, so both tangent lines are perpendicular to segment AB, so the lines are parallel to each other. Okay, if two lines are perpendicular to the same line, that means they're parallel to one another. Okay? All right, the converse is also true. Okay, so you kind of like, if you flip the statement around. So if a circle has if you draw a radius to a tangent line and stuff like that, then you have a right angle there. And if you draw, if a line is perpendicular to a radius of a circle at a point on the circle, then it is a tangent to the circle at that point. Okay, so it goes kind of both ways there. Okay, and again, we won't do the proof here, all right, but I do want to jump into our last little relationship, okay? And then we talk finally now about circumscribed angles, okay? A circumscribed angle is an angle formed by two rays, so that means they have a starting point and they go on infinitely in a single direction. So here, here's a ray, right? Starting point goes on forever in one direction. Starting point goes on forever in one direction, okay? So it's an angle formed by two rays from a common endpoint, so there's our common endpoint, that are tangent to a circle. Okay, so this is a circumscribed angle. The circle fits just inside that angle so that the one side of the angle touches the circle at a tangent, or point of tangency, and the other side of the angle is tangent to the circle. A circumscribed angle of a circle and its associated central angle are supplementary. Okay, so here's our circumscribed angle right there. The associated central angle here is this angle right there. Okay. So we know that this angle and this angle are going to add up to 180 degrees. All right? What do we know about this angle right here and this angle right here? They're going to be what? What measures will these be? Well, what do we have? We have a tangent line. And what is this segment? A what of the circle? It goes from the center to a point on the circle, so it's a what? It's a radius. And what kind of angle is formed where a radius and a tangent meet? What kind of angle is this right here? It's a right angle. Right? And same thing here, radius and a tangent line. So what kind of angle? Right angle. And so that's kind of like basically the proof for why these two angles are supplementary. What kind of shape do we have right here? What shape is this? It's got four sides and four angles, so it's a quadrilateral. Okay, and actually it's more specific than that. What maybe more specifically could we call this shape? What specific kind of quadrilateral is this? It's a kite. Yeah, it is a kite. Okay. So anyway, since these two angles are right angles, that means they're 90 degrees. They both add up to 180. Subtract that from the 360. That leaves that these two angles have to both add up to 180 themselves. So in other words, they're supplementary. Okay, and that's kind of like the proof about how that works out there. Okay. So those are your circumscribed angle theorems. So now we've got central angles, which are equal to the arcs that they cut out, right? We got inscribed angles, which are half of the arc that they cut out. And now we have circumscribed angles, okay, as well, right here. That's a circumscribed angle. Okay, where the circle fits inside of the angle like that. All right, questions on any of that? All good? Okay. Cool. So we'll stop there. Believe it or not, I think I'm gonna cut it there. I know you guys, you're like, that's really quick, but yeah, I think we're gonna do that just so that way those of you that haven't taken the quiz can get a chance to take the quiz, okay? And ask any questions you want to before you start the quiz and stuff like that. All right. Your assignment, what I'm going to give you guys, I think I'm also going to put a 10 marks up as well. All right. But for right now, I'll just give you the book assignment and then I'll put the 10 marks up. The 10 marks is not up just yet, so that's why. On page 809, numbers. Okay, let's go to, let's see, start at 4 here. Four through 6. Oh, one thing. I feel like we missed something. Oh, okay. Yeah. Okay. Sorry, I did want to mention one other thing. Now I'm seeing it here. Okay. That we like a property that I just wanted to hit at real quick. Okay. In a circumscribed angle, it's on page 808 here. In a circumscribed angle, okay, like formed by the two tangents there. All right. The length from K to M and from K to N is going to be congruent. Okay. And the reason for that, well, let's think about this here, right? If I were to kind of like connect K to C like this, okay, what shapes do we create right here by connecting KC like that? Two triangles, and specifically two what kind of triangles? They're right triangles, right? Because again, we have a tangent and a radius intersecting, so that's a right angle, that's a right angle. Both of those triangles also share the what? What we call this side of our right triangles here? Hypotenuse, and they also both share a radius. And so these two triangles are congruent by hypotenuse leg. Okay? They're congruent by hypotenuse leg. Hypotenuses are congruent, the legs are congruent, and so therefore the two triangles are congruent. Thus, K to M and K to N are going to be congruent as well. Okay? So that's another thing I wanted to point out. When you have a circumscribed angle, the distance from K to one point of tangency is the same as the distance from K to another point of tangency, the other point of tangency there. Okay. Sorry. Back to, because I was looking at the homework, I was like, oh, we need to talk about that real quick. All right. So let's continue here. Okay, so now that you know that, all right, I'd like you to try 8 and 9 as well there. Let's do 12 through 15. I think I'll stop it there. Okay, so just that. Right. So that'll be your assignment for you guys to work on here in class. I don't assume anyone, well, if you don't have the quiz to work on, then you should be able to get done. No problem here in class. Okay, and for the rest of you here, I'll give you an opportunity to kind of like ask me any last minute questions you might have before we get started on the home, or before